Welcome to today's webinar. My name is Arya Hakimin, application scientist here at CTherm. Today, our webinar is going to be focused on the analysis of thin films, specifically looking at thermal conductivity, as well as other thermal analysis such as CTE or coefficient of thermal expansion. I'm going to be kicking us off here today, but I will be joined on the later side by my colleague Alex Mann. Who's going to take us through some of the other thermal analysis techniques relevant to thin films. So I'm going to kind of have a little bit of a two-parter of today's session. So I wanted to just give us a quick intro for those that may be new to CTherm, who we are, what we do. So at CTherm, our main focus is really on thermal conductivity, specifically looking at the transient class of measurement technique. Our goal really is to simplify thermal conductivity testing for the materials of tomorrow. And we do this through the advancement of various transient methods on our Trident platform. So you can see here, Trident, this is our core flagship instrument. It is a modular device, so it brings together 4 different methods for thermal conductivity and related property characterization. The idea here is giving you options to pick and choose the best method for the task at hand. And this quote here is one that we like to reference from Abraham Maslow: when all you have is a hammer, everything looks like a nail. And really this embodies the idea behind Trident. One of the biggest sources of poor measurement data or issues with results is when you're trying to take a method that may be really good in one area, one kind of testing condition or sample type, and then trying to apply it to a broad range of materials that it may not be designed for. So again, with Trident, you have more of this toolbox approach to pivot into the option that's most appropriate for what you are looking to do. Now, for those that maybe you're new to thermal conductivity, or maybe just looking for a general refresher, towards the end of last year, we did update our method selection guide. So this is a fairly recent update, kind of covers really all of the transient methods that are available on Trident, as well as other methods that are available in the industry. So if you're looking to dive into a little bit more detail on some of those different options, this is a really nice free resource available that I'd recommend taking a look at. But all that being said, kind of done with the kind of little intro. Now we're going to jump into our topic here today, which is thin films. So, when I was looking through kind of, I say recent work that we have done in the past year, but then also kind of what's been published out there and maybe some things that are kind of popping up in the news. Thin films are certainly a hot area for a variety of different reasons. The whole miniaturization or trying to decrease the weight of different systems, thin films can really be an enabler for many of these different technologies, ranging from, your standard electronics to maybe some of the things that are going into aerospace or defense industries. Another interesting point that I've seen is a lot of work on optical-based technologies. Some of these thin film advancements are really helping to, whether it's more like augmented optical or, just reducing glare, enhancing clarity on different as coatings. Certainly some interesting things going on there. Energy efficiency applications. So, whether this is, energy harvesting, energy storage, batteries, solar cells certainly have a play with thin films. And then another one, maybe a little bit more niche, but certainly something that I've seen quite a few, I'd say, areas of research being done in is on the biomedical or medical-based devices, different types of protection coatings for implants or more flexible electronics. These are all different, some different areas where thin films are certainly at play. It's by no means, the all-encompassing, but some of the more common ones in terms of theme that we've seen over the last year or so. I picked this one also. I was just kind of looking. This was from a post from MIT News, kind of what, something kind of popping up in that's quite popular for thin films. So this was towards end of last year, but kind of looking at utilizing thin films as again enabler for lightweight, but specifically on night vision technologies. So kind of combining that lightweight miniaturization with some of those optical. I believe this has some variety of different applications, but certainly in defense, and kind of some of the AI or sorry, augmented reality tools that exist there. But they're also commenting that, with more of these advancements, this specific method that they're looking at could be applied to wearables, computing elements in a variety of different ways. A quote from one of the students working here is, this thin film considerably reduced not only the weight, but also the cost, making it overall a better, more easily integratable technology. So, like I said, certainly a lot of new and interesting developments going on in this space. So thin films, in terms of where they're being used, is quite wide ranging. Now, coming to the actual testing of films, and I'm going to, of course, focus primarily on the thermal conductivity side of things here, but there are certain challenges that exist, right? Being a thin film, small format, very miniaturized sample, your traditional steady state methods and many of the more basic, even transient approaches, your thickness requirements aren't really going to be met. So there is some fundamental challenges here just based on what many methods will require as a minimum to be able to take a valid measurement. And these are just going to be some of the points that we'll talk about going through in today's content. Another big one is anisotropic behavior. So, the difference in versus through plane thermal conductivity. Sometimes this is just anisotropy is present, maybe it's not desirable. Other times groups are really pushing to introduce high levels of anisotropy. But in either case, if it is present, certain techniques, again, others may be, some may be directionally dependent, others may average out over a larger area. So if you are looking to separate out and quantify those, there may be some specialized approaches that are needed. Substrate effects. So, talking about thin films in terms of coatings, excuse me, or, when your film isn't a freestanding, it has to be on a backing material. So that substrate impact can potentially introduce errors in the measurement, again, depending on what type of approach is taken. So from that side as well. And then lastly, overall, in terms of thin films, one of the big things is the overall size and potential defects that can be introduced, whether that's in the formation of the film or how it's being used in application or long-term wear. These are all little things that can come in and impact the overall transport efficiency of that heat within the system. So it's something that should be well understood. So all of these together present certain let's say roadblocks in terms of how you would go about testing. So need to look at what tools exist that can help overcome some of these potential challenges. But overall, before we go into some of the different methods, we're talking about thermal conductivity, but why does it matter? Across a broad range of material types, thermal conductivity, you'll see some similarities in that, and true for thin films as well, but very much ultimately used as a benchmarking metric for the overall performance and the reliability. And really depending on the application space, can have quite a big influence on that overall system. So whether, again, you're looking at electronics, more insulative coatings, or thin films, or otherwise. Now, I'll break it down into two. So you have your high thermal conductivity applications for more of these thin films. And, I'd say by and large, the big one is going to be TIMs, or thermal interface materials. So of course, any type of electronic introducing, or I should say generating heat, we have to have a way of dissipating that, or efficiently removing that from those potentially sensitive components. and TIMs being in quite a variety of different forms and shapes and sizes. Thin format TIMs are certainly something that is being heavily investigated in many of these new technologies that are coming out. But there's also the low thermal conductivity side. For thermal electrics or thermal barrier coatings, different packaging applications, there are certain scenarios where you're actually looking to more insulate certain systems. Maybe it's for protection, or again, maybe that's your performance metric. You're targeting lower conductivity as your kind of ideal situation. So you can see both. So the high and the low K materials in thin film formats have different use cases depending on which situation we're in. This was a publication by Yang et al. In 2025. I kind of pulled this just interestingly because one of the highlights, this was just kind of on the main summary page, kind of noting here the thermal conductivity was decreased from about 0.6 to 0.22. And that was their desirable outcome. So, in many cases, a lot of what I more regularly see is groups trying to bump up that thermal conductivity. Again, a lot of those thermal interface material situations, but again, certainly some scenarios where kind of going the other way is more important. And specifically for this application, for those that may be in this space of thermal electrics, you'd be familiar with the thermoelectric figure of merit. So the equation here, you can see kind of the different terms, but where thermal conductivity comes into play when you're actually kind of doing this calculation, being in the denominator here, we're trying to have a high ZT value, but to get that, we're looking for low K systems. So in the context of these thermoelectric applications, again, that lower K material property is more desirable. So again, just kind of a little bit of a tidbit of information there for those that may be kind of entering into or working in this space. But this brings us to, okay, we know what we're looking for, we know the sample type, but how do we go about testing it? So on the Trident system, there are a few different approaches that we'll look at here today. First one being with the Flex Transient Plane Source, or TPS. So the TPS, you can kind of see a picture of it here. This is a very thin, flexible, double-sided sensor design. But specifically, we're going to be looking at the thin films utility. So the thin films utility, as described in the ISO standard, so ISO 22007-2, again, for folks that are interested in TPS testing, this is a really great resource to take a look at if you don't already have it. Really kind of outlines what this can do for you. So the thin films utility, this allows us to do a through plane measurement of micron range thick samples, typically targeting I'd say more on the lower conductivity side of things, like sub 5 watts per meter Kelvin as kind of a general rule. Really important when you're doing testing with the thin films utilities that your materials do have a kind of a well-defined and uniform thickness. Part of the actual measurement procedure is to use the measured material thickness as an input. So of course, the more control and consistency you have over that, the better your outputted results will be. And I wanted to highlight that the TPS thin films utility, of all the options of TPS testing, it is, I would say, one of the more different approaches, in that involves a sequential layering procedure and subsequent measurements that are tested. It's not just one singular measurement. And it kind of looks something like this. Your overall setup, you actually have your sensor in conjunction with a conductive backing material. So this is kind of like your blank or your base measurement. So the first test you actually run with TPS thin films doesn't have any material or thin film at all. You're actually just taking your blank. You would then take your setup, mimicking kind of what we had in our blank, but now adding in a layer of that film. You would then repeat this a second time with a second layer. And overall, what the testing procedure looks like is you have your sensor with different amounts, starting from 0 to 1, 2 layers of your film. And it allows us to build out a temperature versus the film thickness linear regression. And based on that data, we're able to extrapolate out that thermal conductivity, again, in that Z direction, or that through thickness of the material. So an application that we saw, I believe this some kind of popped up at a conference one of our colleagues attended last year, but they were talking about the use of thin films in e-motors. Really kind of highlighting the use of a specific one, actually Nomex. Nomex, if you're familiar, very commonly referenced for its, thermal and electrical benefits, and different kind of components of these, e-motor systems. So, these types of like Nomex or like some other kind of related materials like Kapton, for example, these are all things that have been very, I'd say, well tested in the past using the TPS utilities. Again, specifically the thin films here. For those that may be interested in kind of just looking at more than a few data points, we actually have like a full write-up on this application note, again, available as a free resource download on our website. But just in the context of like the thin films utility, this is certainly a very, I'd say, one-to-one capable approach that many groups are opting to investigate for. Again, being a transient approach overall, still very quick in test times, a nice way to accelerate some of that testing capability in a generally easy way, considering we're looking at a thin film material with known challenges with some more traditional approaches. Another use case for the, I'd say the TPS thin films is looking at thin films used in fuel cells. My colleague Genesis, who's a lab manager at our thermal analysis groups, was doing some work with this last year, but kind of looking at some different, let's say, layers of the different systems that are involved here. So whether you're looking at membranes or some of the catalyst layers or the GDLs, these different materials, thin film in nature, thin in nature, can be potentially very relevant in terms of their heat transfer performance. And really the through play is what that was targeted here as the primary driver of interest as it relates to the reaction system as it would go through these different layers in the fuel cells. So some of the testing that was done, again, using the TPS thin film setup. So here you can kind of see what the kind of half of what that setup looks like, your metal kind of conductive backing, the sensor, and you can see the top sample placed over top. Kind of another example data set that was looked at here. So comparing two different materials, a neat GDL versus an MPL plus PTFE sample. So you can kind of see how they compared in terms of material selection for the system use case. But then actually kind of a second set of these materials where it was actually densified and kind of seeing does that significantly impact that performance of the material. And as we can see, and as you may expect, the more densified the material is, the better that overall transfer networks will be available and overall resulting increase in thermal conductivity. But being said, these different sample types, being thin films, but in different application spaces, some different capabilities there with our thin films on TPS. But when I was talking about the thin films system, that was, of course, I mentioned it's a Z direction or through plane measurement. There is certainly some interest in the in plane. So how would we go about assessing in plane thermal conductivity of some of these films? So again, how would we do this on Trident? Again, I'm going to kind of look at the TPS here, but this time, instead of looking at the thin films utility, actually pivoting into the slab option. So slab is, again, a different functionality of TPS. It's an in-plane measurement of the material as it relates to the heat spread rather than the heat transfer through. With the slab utility, generally recommended for higher K sample types. The ISO kind of stipulates 10 watts per meter Kelvin or higher is ideal, usable down to materials that are above 1 watt per meter Kelvin. But again, generally in the higher K range. There is some similarities between the thin films option and the slab in that they both need the input of thickness. So how thick the sample is part of that testing procedure. Excuse me. So understanding having a well-defined thickness is going to be ideal and important for best results. And similar to the TPS thin film setup, there is a specialized slab setup that is done. And this is what's really allowing us to get at that in-plane measurement. So your slab setup You have your sensor with your two test pieces, but now your backing material, it's not a conductive sample like we saw with the thin films. It's actually an insulative backing material. Because the idea here of what we're doing is the sensor, this is where the heat's being generated. We are assuming this heat is traveling through the thickness of these very thin samples very quickly. So of course, it's going to hit this boundary condition. And if you're familiar with transient approaches, in the more basic or bulk style measurements, the assumption is that no boundary point is reached. It's viewed as a semi-infinite medium. But there's a little bit of some differences in how the data is interpreted here, where this backing, this insulative backing, is here to essentially halt that heat transfer in the through thickness direction and then promote the spread in plane. So slab and thin films, I kind of describe those somewhat being opposites of each other in terms of some of their setups and some of the directionality based on the measurement. But again, utilizing slab here for some in-plane high K measurements of some heat spreader applications. So this was some work again that was worked or developed in the past year or so. So looking at measurements of very conductive, very thin graphitic materials. So this was some work that was generated. You can kind of see a few different groups of materials. So there's some flexible graphites, flake style versus some pyrolytic foils. Overall, testing some of these pyrolytic foils, again, very thin micron range, we were able to get some very exceptionally high K results. This is a trend that we've seen more and more, very high, highly anisotropic with very high in-plane conductivities. It's certainly something that over the past, I'd say definitely 6 months, there's been multiple opportunities that we've worked with groups on where this was a kind of a key focus for what they're looking at. Now these samples down here, while they weren't, into that 1,000+ watt per meter Kelvin range, still, a few hundred watt per meter Kelvin, still quite high in the grand scheme of things compared to many other materials in this space. But again, to be able to assess these materials specifically, this is where we needed the slab utility because we're looking more at that in-plane heat spread as the more dominating property of interest for these groups. So as a quick recap here on the TPS, the thin films utility is going to be really great for those lower K materials where through plane is of interest. Again, it utilizes a conductive backing material, and the overall kind of flow of your measurement involves a multi-point measurement approach. And again, slab, like I said, somewhat the opposite. You're dealing with more higher conductivity materials in plane. You're using an insulative backing material, and instead of it's just done with one singular measurement. So I'll just kind of highlight that for folks like interested in this space, or maybe you want to deep dive a little bit more on TPS. There's certainly a lot more information that we could go into on this, but just wanted to give you that to kind of maybe get you guys thinking about this as a potential option for some of your work. Now, we talked about TPS, and one of the other methods available on Trident is the modified transient plane source. So this is Seatherm's proprietary sensor design, a single-sided sensor. And for those that may be familiar with MTPS, you may be wondering why I'm bringing this up for thin films, because many will know that your minimum thickness requirements, it varies depending on material type, but typically we're in that millimeter range, right? So fundamentally, there's a gap there if you're looking at some of those micron range thicknesses. So this is true. Your sample thickness in the standard setup, you have to cover the length and width of the sensor face, which is about 18 millimeters in diameter, with a thickness in that millimeter range. However, there are some options here. One of the main ones is a stacked approach with some of those thinner samples, layering them up to achieve your desired or minimum thickness requirements. Now, I will highlight this is not suitable for all materials, especially once you get into some higher K samples. The contact resistance between those layers starts to result in quite a bit of error. The quality of those layers, if they're very flat and planar, or maybe somewhat adhesive in nature, you can get really good kind of stacking. Great, but when you have some more uneven, non-uniform surfaces, that's where it becomes a little bit more problematic. But this is something that we've done with good success in the past, and I wanted to highlight this kind of application highlight that we did in conjunction with Tessa Tapes a few years ago, where we're looking at testing thermally conductive self-adhesive tapes using the MTPS. And in this study, really these samples are designed for, e-mobility applications. They were thermal conductivities in the range of about zero point 0.7 to 2 watts per meter Kelvin was kind of their products of interest at the time. But their thicknesses, some samples were in the millimeter range, but they did have quite a few that were micron thickness, so below what we technically needed. So again, this is where that stacking came into play. But the whole challenge and the reason we actually did this project together was they were running into some issues checking their materials in situ. So kind of taking the samples, putting them in a system, kind of like turning it on and measuring how much heat was actually being generated and how efficient those tapes were at transferring the heat. And when they were comparing their materials to competitor products that had a spec technical datasheet value, something wasn't lining up for them. So we kind of came in as a third party to assist with this investigation. And what we ended up using was our MTPS to test a couple of their samples, one of the competitor samples, room temperature, and keeping as many things controlled and fixed as we can. So under a defined weight loading of about 500 gram force. And essentially what the data looks like, you kind of see it here. The two TESSA samples that we ended up testing, our results lined up quite well with the technical data sheet. One of them came actually a little bit higher than what they had previously expected. So this wasn't shocking to them. This was kind of in line with what they were expecting. But this over here, this was really what kind of helped answer some questions for them, because like I said earlier, in situ, they were seeing some ambiguity between what the technical data sheet was saying and what that product was actually providing as a kind of an output. And when we did the test, we were showing that the actual thermal conductivity was significantly lower than what was kind of on that spec sheet. But this really validated what they were seeing with some of the issues there. And the whole, I'd say, benefit behind MTPS in this context is that it's a very quick and easy way to easily compare, if you've got multiple different kind of similar materials and you're wanting to understand like where are those highest performers, where are those lower performers coming at. It is a very simple approach to kind of understanding this. And for them in their application, this type of discrepancy can have significant impacts on the overall temperature of some of these EV-based systems. So it's really important for them to be aware of where they are falling in terms of general ranking with some of the other competitor products. This here too, I just wanted to share kind of a quick example. Another group kind of working in flexible thermal electrics. Again, kind of referencing the use of the MTPS. So this is some work coming out of Singapore and China. So in this study, they were looking at these polypyrrole nanotube films, kind of two different variants here. The thermal conductivity was tested using the MTPS. And interested in this one, they're actually looking at the thin film K as a function of temperature. So we kind of just skip to the results here. You can see again, a very nice way of comparing, a sample to another material, kind of checking its performance across different temperature ranges. Other variables that can be looked at is like different applied force loads. Humidity conditions is something we've seen pop up as well. So kind of these different kind of investigations. The MTPS certainly does have some play there if you can get around that stacking and thickness requirement. Ultimately, I kind of always like showing an SEM image of the samples if we got them available, but you can kind of see the general gap between the two different samples here was ultimately related to that quality of the film. So again, kind of mentioning earlier some of those challenges with like defects in the structure. These are things that you can visually inspect, but really being able to quantify that through a measurement really allows you to kind of have a strong basis in where that performance is going to be. So as a quick recap here, MTPS, again, really quick, easy way, really great for high throughput environments where you're comparing a multitude of sample types. The benefit here is that there's no kind of settings that the user is adjusting. It is very much a plug and play option. So it really negates any introduction of user bias compared to some of the other methods that are available. Now, again, like I said it a few times, just to make sure it sticks, you do need to achieve that minimum thickness. So if you can stack, there is a viable path forward. Of course, if not, that's where you may want to look at some of the other tools. So again, generally okay for lower K, like a lot of polymer-based films, like adhesive, things like this, we've had really good success in the past with that. Okay, but from my side, I hope that was a hope everyone got some good information out of there on the thermal conductivity aspect of things. At this point, I'm going to turn it over to my colleague Alex, who will take us through some of the information here on Rigaku's thermal analysis. So thanks, Alex.
Great. Thanks, Arya. As mentioned, I'm just going to go over some of the other thermal analysis options that are available within films. So we're going to start off with some instruments from our partners over at Rigaku. So essentially, there's going to be three instruments, the main one being the TMA, of course. So we're going to start off with the DSC, the differential scanning calorimetry. This is a really good measure for energy-related events. Moving on, we have our STA, or our simultaneous thermal analysis. This really couples TGA, which is change in mass, with our DSC, change in energy. And then lastly, we're going to look at the TMA, which is thermal mechanical analysis. And this is anything related to thermal expansion or contraction. So how does this relate to thin films in this thermal analysis? Well, our DSC, we look at energy, we can look at the temperatures, the enthalpy associated with things such as melting, crystallinity, glass transition, as well as specific heat capacity. Moving on to our TGA, which is our mass change, we can look at decomposition, whether it's, exo or endothermic. Is it primarily pyrolysis or is it combustion? We can also look at filler content, inorganic versus inorganic when we burn it, as well as some stability measures such as oxidation induction time. Lastly, for our TMA, where we're looking at expansion, the most popular one, of course, is the CTE, coefficient of thermal expansion, great for predicting how much it'll expand. As well, we can also measure a glass transition, and as well, we can see cold crystallizations using the TMA. So the reason we're going to focus a little bit on TMA here is because it actually requires a special attachment or holder to do this. For the DSC and the STA, the instruments don't require anything special. They can just be run as usual. It's more in the sample preparation. So Rigaku's TINFE, or TMA, specifically for the thin film. So not only can it be used for thin films, but there's also foils, wires, fabrics, anything that is within the 10 to 200 micron range. So specifically for thin films, we can go all the way down to negative 150, which is good for TGs of fluorinated polymers, all the way up to 600 degrees Celsius. Its primary use is for polymeric thin films, so high temp of 600 is more than plenty. And then because it is a thin film, we're going to need to apply a little bit of a load to keep it from sagging or buckling during the measurement. So we can apply a tensile load as low as 1 millinewton, or we can go as high as 1,000 millinewton. And lastly, for the film dimension, as I mentioned, anywhere between 10 to 200 micron is good. After that, we'll have to switch to regular TMA. The film length, there's three options. We're going to have 10, 15, or 20 millimeters in terms of length. And then our width is going to be limited or fixed at 5 millimeter. One really interesting thing about the Rigaku TMA is that it does have the option for a humidity generator. So this goes beyond the standard ideal condition. And now we're bringing it out into the real world application. We can add humidity. So our inlet stream to the instrument can have anywhere from room temperature to 85 degrees Celsius in terms of temperature. And then from that, our RH, our relative humidity, can span from 5 to 90%. So what this does is we can now determine how much it'll shrink or grow whenever we take away or add water. So the coefficient of hygroscopic expansion. Now, this is pretty useful for things such as fabrics and hygroscopic thin films, but we've also seen an interest in metallic foils under humidity as well. So real quick TMA methodology and why the thin film needs something different. So for the standard TMA compression, our sample down here shown in blue, it sits inside of a hollow support tube. On top of the sample rests our detection rod. As the sample expands, it pushes the detection rod up, which is then registered by the detector or the differential transducer here shown. So it is a compressive. So now, if we move over to the thin film, if we compress a thin film, it's just going to buckle. So now the way it works is the thin film is clamped using the two red clamps you see there. The bottom clamp is actually outside of the support tube and is pinched or hooked. Then the detection rod now pulls it upwards. This is where we get the tension. So now when the thin film expands, the detection rod, again, it'll go up and it'll get detected by the differential transducer or the mechanism. So in order to get our thin film inside of the clamps, we have a really nice jig here. Starting from the very bottom, we have our base, which is machined to a high degree of accuracy. And essentially what we'll do is we'll insert our lower brackets in our spacer, then we'll tighten it to make sure everything is nice and snug. Then we'll insert our sample on top. Then we'll add the upper mounting brackets, close it all up, then tighten our fixture again. And the reason this is done is so that one, the sample is a very precise length. So either the 10, 15, or 20, it's exactly one of those lengths. And also we want the clamps to be flush and the sample to be straight because we don't want anything crooked or twisted or bent. Here, we're going to show just a quick video, 20 seconds of what it looks like to load the sample. As you can see here, the detection rod is free. It can move up or down. So we place our clamps. Then we're going to hit the button to allow detention. So the detection rod is going to bring it up. It's going to pinch or clip on the bottom or outside of the support tube. Then lastly, the little metallic foot is going to be adjusted so that it holds it in place. This is just in case the thin film stretches, breaks, melts, or anything. We don't want the clamps to fall down into the furnace. It's really important when you're setting up your sample that you're not applying too much force, that you're stretching the thin film, but also you want to apply just enough so that there's no sag or any, buckling of the thin film. So in order to find the ideal tension range, it's just kind of start off slow and gradually increase the force until it's flush and there's no kinks or bends or bowing. So this is what your standard TMA thin film graph is going to look like. This example is thin film polyether ether ketone, or PEEK, as we show here. We see there's two primary regions. The first region on the left side of the graph is going to be the glassy zone or the vitreous zone. And as we increase, the expansion will curve to a new zone. That is the rubbery zone. And then if we take the tangent of each of these zones, we combine them and we'll get a pinpoint location. That is where the glass transition point occurs. So PEEK, for example, is very chemically resistant. It has high mechanical strength, especially at high temperatures. So an example of its use would be the flexible printed circuit boards in electronics. Then next, this is a little special custom test. So what happened here is this was done on a copper thin film or foil in air. And essentially, instead of doing the classic ramp up and down to get the CTE, what was done was that an isotherm was held every 100 degrees Celsius for an hour. As we can see starting at the bottom, the first isotherm, we didn't really see any change during the hold, which is expected. As we go to the second one, again, we didn't really see anything during our isotherm. But now at the third one, at around 300 degrees Celsius, we start to see that even though we're not increasing the temperature, we're still getting some expansion. And then now we go up to 400. As we can see, we're getting notable expansion, even though we're not increasing the temperature. Lastly, the last iso, huge amount of expansion. And then as we cool back down, we see that the sample has been permanently damaged. And this is because as the copper, reacts with the air, it tends to oxidize. So as we saw, it turns brown or black. This is the same test, just looking at it from a different point of view. You can see on the x-axis, we have temperature. So the first isotherm, it's really not noticeable because nothing happened during the hold. The second isotherm, we can kind of see it, but again, really nothing insane happened. Now, as we get to 300, third isotherm, we can start to see the jump, which occurs because we're holding, so the temperature isn't increasing, but we're still expanding, which is why we get this vertical line. The fourth one, we can clearly see that something is happening. We're getting some irreversible damage. And then lastly, at the 500, we can see a lot of expansion. We're really damaging our sample. And then interestingly enough, on the cool down, it doesn't go back to where it initially was. Because it's been damaged, we're left with 140 microns of permanent deformation. So this is kind of how I took the TMA, and it was used in order to get something more, insightful or practical, and not just a CTE number. So we're going to move on quickly. We're just going to touch base on DSC and TGA of thin films because I mentioned that it's the same thing, but we have to do some sample prep. So the sample preparation for DSC or TGA, again, there's no special attachment. You just use the instrument as you would normally, but the key is a sample prep. For DSC especially, they recommend taking a punch and cutting out a piece, which is the exact same size of the inner diameter of the crucible. What this does is it allows great surface contact because we're touching the entire bottom of the crucible. But one of the issues is that because the films are so thin, we can only get around 4 milligrams for this specific sample, which is a 25 micron thick thin film. So if we're doing something where we need a lot of mass or we need higher resolution for like a TGA, well, now what we do is it's actually recommend take the punch and just stack a bunch of these pieces on top of each other. And one of the things we have to keep in mind is when we do this, it's highly recommended to now crimp the pan. So what this does is that you put the same um, metal that the pan is, you put the cap on, and you shove it down and you curl the outside of the pan so that it's pressing down on the cap. So here's a little schematic. So for the left side here, we have our open pan with a stack. And as you can see that in between each layer of the thin film stack, there's an air gap. So what this does is it decreases the density of the pan or of the system, and it lowers the conductivity. So whenever our energy has to travel through the sample, through the crucible into the sensor, we're not going to get the best signal. It might be a little delayed. So again, on the right, when we crimp the pan, we squeeze all the layers together, and then using the edge or the rim of the pan, crush it down to hold it in place. As you can see there, that's what it looks like, where the edges are curled down around and the pan is getting pushed on by the lid. This gives us the best signal and the best results. Just a couple quick examples. So we're going to start off with the TGA DSC of PTFE, or Teflon thin film. So we have two things going on here. We have the TGA weight loss and the DSC energy. We're going to start with our blue line. As we go across, we can see a little endothermic bump at around 325. This is the melting of Teflon. And then after that, we see that we have large, very large endothermic. So what this tells us is that our Teflon is going to melt at around 325. And then after that, when it decomposes, the primary method of decomposition is going to be pyrolysis because it's endothermic. When we look at the TGA, we see no mass loss through the first event because it's a melt. But then a little bit after 430, we start to see the TGA curve down. This is where our mass loss really begins. And around 530, it really ramps up. A common use of Teflon is nonstick frying pans. It's resistant to heat, it's very slippery. But what we see from this graph is that our frying pan range would be good from room temperature all the way up to around 330. Then the Teflon coating melts, so we have effectively damaged our pan. And then if we keep going and we reach around 430, now all of a sudden the coating itself is decomposing. So we went from ruining the pan to now emitting toxic Teflon decomposition fumes. So just a real quick summary of what went through on my part of thermal analysis. TMA, you're going to need a special tensile loading attachment to do your analysis. And then for the DSC and TGA, nothing overly special, a cheap circular punch. And if you do for your, method need to implement stacking, then highly recommended, please crimp the pan. Thank you.
All righty. Thank you, Alex. So folks, yeah, kind of wrapping things up here. Just gonna go through a few final outro slides. If this type of content was interesting, we put these on regularly throughout the year. We do have a range of additional resources available on our website. So some of the past webinars, again, these are all recorded and posted after the session. So you can certainly check some of those out. We also have a tech library available. So many of the kind of publications or like application points or documents that are featured, they will be available where you can find the links to those on the website. So definitely check that out. I wanted to make note of a couple upcoming webinars that we do have scheduled already for the start of the year. Towards the end of January, I'll be joined by folks from the Thermap Solutions, who are actually going to come and talk a little bit about a different measurement technique, more on the frequency time domain thermal reflectance category of testing options. So it's going to be a really interesting, very unique discussion there around how and where those techniques are employed. So again, that's coming up at the end of January. And then towards middle of February, we're going to be doing another kind of like application focused webinar on testing performance in the space of wearables and humanoid robotics. Again, kind of a lot of interesting things going on in this space right now. So kind of touching on where thermal comes into play in those situations. As was kind of mentioned here today, so CTherm, of course, focusing on thermal conductivity, but with our partners, with Rigaku, Metrovib for different material testing options. Alex touched on a few of the Rigaku capabilities. But we also have our TAL group, Thermal Analysis Labs, as a contract testing division. So folks that maybe you need some data, but you're not really ready to bring something in-house quite yet. If you're looking for a group that can offer testing services, certainly something that we're happy to provide. Um, for either of the Trident or the Rigaku products, or just generally like testing discussions, if you were interested in kind of maybe doing more of a one-on-one with us and kind of going into it in further detail, we do offer free technical consultations. These could be booked. You just reach out to us, kind of say you're interested in kind of discussing some options, and we can certainly arrange that, kind of go over the theory in more detail, give you a demonstration even of how you'd set up and run the instrument. So these are all things we're certainly happy to provide. Um, and of course, if you're in the kind of the shopping phase looking for budgetary information and you're just trying to kind of compare some numbers around there, see what would work for you, certainly something that we're also more than happy to send along. I will just always kind of like to flag this. If anyone on the call right now is from the academic sector and you are maybe looking at some of these options, definitely if you do reach out, make note of the academic discount program. So we do offer some nice benefits, more than just like a top line discount on the instrument, different warranty, support packages, a bursary, and also some testing credits. So yeah, definitely feel free to kind of mention this in particular in your reach out. Um, for those that aren't doing it already, I would ask if to give us a follow on LinkedIn. This is where we post all of our upcoming content, the latest and greatest, whether it's webinars, blogs, where we'll be for conferences. So give us a follow on there if you're looking to stay up to date with us.